Hi, I'm Ravi and I'll be talking about STATuner, a framework we developed to efficiently tune CUDA kernel launch parameters. Heterogeneous system is a computer system where computation is performed on multiple processors, example CPU and GPU, as against a homogeneous system where the computation is employed only on CPUs. Heterogeneous systems have gained wide popularity in high performance computing world in recent years as GPUs upkeep the promise of high throughput on parallelizable sections of the code. The kernel code runs on GPU and the host code runs on CPU. Numerous instances of the kernel code are run, operating on different sections of the data, and each instance is called a thread. Before execution, certain number of threads are grouped into a block called as a block size. Each block runs on a GPU multiprocessor utilizing its resources. As it happens, block size plays a key role in performance of the kernel code on GPU. Wide variation in performance can be observed with variation in block size, as seen in figure 2. Hence, it is very important to select the optimal block size to launch a kernel on the GPU so as to get best performance, especially if the runtimes are in minutes or hours. We propose a solution to predict the optimal block size based on supervised machine learning and hence reduce effort related to tuning CUDA programs. Occupancy calculator is available to help programmers select the optimal block size for a kernel. Occupancy is defined as the number of blocks actively running on a GPU multiprocessor, and it is advocated that block sizes which give highest occupancy will result in best performance on GPU. However, from our experiment we find that occupancy does not map very well to performance. From figure 2, execution time and occupancy are plotted on whole spectrum of valid block sizes. As we see, the trend of higher occupancy and lower execution time does not hold very true here. We propose a novel approach for predicting block size using machine learning on key static features of the kernel, and this framework is called STATuner. The static features of the kernel code are extracted by a LLVM pass. Static features taken into consideration are total instructions, loops, registers, branch instructions, usage of shared memory, and memory instructions. We use support vector machine as our preferred machine learning engine as it is very easy to use and configure. Static features for application kernels are extracted and labeled with optimal block size to input into SVM for training. Once the training is complete, the static features for any new unrelated application kernel can be input to this trained SVM to get predicted optimal block size. The prediction workflow is shown in figure 4. The kernel code is extracted from CUDA code and converted to LLVM IR by LLVM pass. Static metrics is extracted from this IR and inputted to the trained ML model to get predicted block size as the output. This block size can be used to compile and run the GPU code, kernel code on the GPU. Training workflow is shown in figure 5. Through manual runs, the optimum block size is obtained for a particular application, which is used as the label for SVM. An example of training input matrix is shown in table 1. As we can see, each row of this matrix corresponds to an application kernel with its static matrix labeled as S1 to S7, and the label being the optimal block size as obtained from the manual runs. We conclude that occupancy does not map very well with performance of the code as advocated. More features of the kernel are required to select optimum block size, and using machine learning, a good model can be developed to solve the issue of selecting optimum block size. We experiment with different SVM kernels and found that radial basis function of SVM gave best results. In figure 6, percentage error is a measure of the relative difference in runtime at predicted block size and at optimal block size. Lower error represents better prediction. We compare percentage errors on STATuner with one label, with three labels, and the minimum and maximum percentage errors from occupancy calculator. We see that STATuner performs almost equivalently or better than occupancy calculator for almost all test application kernels. We see that average percentage errors of the models on these applications from occupancy calculator of 6.6% and from STATuner, that is our model, of 4.4%.